Now, let us apply our knowledge to some practical issues. Preparation of simple solutions and serial dilutions of those solutions. Again, you can find all this material in chapter. So, first, I want to make solution of sodium chloride, just usual salt, with concentration 2.0 grams per liter with analytical quality. That means highest possible precision of concentration. For that, I need to start it with finding a good sodium chloride. I can try very expensive sodium chloride with 99.999% concentration. I can stop with 99.99 as well. That's reasonable. I do not want to take 99% ACA reagent, even though it looks very beautiful, because 99% purity is not enough for me. We'll see why. My tools will be usual analytical balances with tolerance 0.1 milligram, that is 0.0001 gram. Next, I'll need a volumetric flask, say 100 ml. Tolerance is 0.08 ml. Where I know that, I can look in a textbook or in any handbook or Google it. Calculations are very simple. Concentrations in gram per liter would be mass of sodium chloride I weighed in grams divided by the volume of the flask. And then I want to convert mils into liters. It's very usual magic number 1000. Now it's easy to see that I need to weigh around 0.2 grams of sodium chloride to make this solution. I will record all my measurements and I will do all my calculation in Excel. So this is a screenshot. Say I was weighing by difference, so my TER was 0, so I had one number, and this is 4-digit number. It's not exactly 2, but that's what happens when you start measuring real things. Now tolerance of this number is 0.1 milligram. That's number from previous page. And by dividing tolerance by mass, we have relative uncertainty, as we had in previous examples. My flask has nominal volume of 100 exactly, but it has tolerance of 0.08, so relative tolerance is visibly larger than relative uncertainty of my weighing procedure. Now, by dividing by 100, multiplying by 1000, I am getting concentration in grams per liters. What is tolerance of this number? I am taking my tolerance here, squaring it, taking this one, square it, and receive the resultive tolerance. You can see the formula right here. That's from formula of uncertainties for a result of division or multiplication. Now, I know relative uncertainty. I can calculate absolute uncertainty. What I'm doing, I'm taking this number, multiplying by this number. That's my answer. I can retype it again so it will be very visible result. Can I do better? Yes. Where my uncertainty is coming from? The largest relative uncertainty is coming from my volumetric flask. So instead of 100 ml flask, I can try a larger flask with better precision, that is 500 ml flask. Let's look what will happen. So again, I'm using the same balances. Now I'm using 500 ml volumetric flask. Tolerance is 0.20. And of course I need 5 times larger amount of sodium chloride. So I'm weighing sodium chloride. I did not make exactly 1 gram, but it's 9997. Tolerance is the same. Relative uncertainty is visibly smaller. What's more important, that relative uncertainty from my 500 ml flask is much smaller than it used to be, twice smaller. So same way I'm calculating the concentration, same formula. And same way I'm calculating the relative uncertainty from this number and this number. And this time it's practically equal to relative uncertainty of flask, because this relative uncertainty is much smaller than this. Only one is important. As usual, that's flask volume. And I have my tolerance that is twice better than it used to be. So my answer has same practically concentration, but twice smaller uncertainty. That was a good idea. Now let's look what if I'll take by mistake ACS reagent rate. 99% here means that there is 1% uncertainty in amount of sodium chloride. It doesn't mean you have 99%, you still have 100%, but you do not know how much impurities you have. So relative error will be 1% or 0.01, and my result will be now 2 plus 0.002, so 1% of my value. Well, for some purposes that's okay, but it is not good enough for accurate analytical work. Next, serial dilution. Serial dilution is the process of making successive dilutions to obtain desired concentration of reagent. Purpose is to transfer accurately small amount of material that are too little to weigh accurately. Here is an example of a process that you could use to prepare standards, for example, for instrumental analysis. So, I wish to prepare a solution containing 2 micrograms of sodium chloride per ml as a standard for atomic emission analysis. 1 microgram is 10 to the negative 6 grams. I have available flasks and I have several transfer pipettes. To obtain a 4-digit accuracy, I want to weigh around 1 gram of pure sodium chloride with a balance that is accurate to decimal place in milligrams, which means 0.1 milligram. Let's design procedure to use pure sodium chloride to prepare concentrated stock solution, from which we can make a series of dilution to obtain 2 micrograms per ml. Now let's look. 2 micrograms per ml is the same as 2 milligrams per ml, or 0.02 grams per liter. Now this quantity is too small to weigh. I cannot weigh it precisely. There is no chance, no balances to do. In previous example, we made a 2 gram per liter solution using 500 ml per flask. This can be a good starting point, but we need to dilute it 1000-fold. Perhaps I need to take a larger 1000 ml flask and weigh a smaller amount, something like 0.4 grams. That will give me 4 gram per liter solution, still 200 times higher than I need. So I'll weigh 0.4 grams, slightly different number because of experimental deviation. Tolerance is the same, relative uncertainty is G. Then I have 1000 liter flask that has very small tolerance and very small relative uncertainty. These two numbers are almost equal, and I can have reasonably good relative uncertainty, and my result can be written in such a fashion. Next step, to dilute 200-fold, we take 5 mils of this solution, so that's our 1 liter flask. We take 5 mils by transfer pipette and transfer it into another 1 liter flask. So concentration of my diluted solution will be concentration of my starting, multiplied by volume of my pipette and divided by my volume of my flask in mils. So it will be 4.4 multiplied by 5 divided by 1000. Units will be, of course, gram per liter. Now, here are my results. Of course, the concentration will be very close to 2. Now, what about uncertainties? Tolerance of 5 mil pipette is 0.001, so relative uncertainty is 0.002. Now, it's 5 times larger than relative uncertainty we had before. This is by far the largest relative error, the bottleneck of our project. In this case, if we have one clear bottleneck, we can use this relative uncertainty directly. If we'll do all the calculation, including all these numbers, we'll receive still 20. You can do it if you want. So using this relative uncertainty and this number, we can calculate uncertainty of our final concentration, and it will be this number. So we have nice concentration with 4-digit number, error in 4th digit, and we can produce this solution with one simple dilution. You can see that we are using large volumes, but this is the price you are paying for high quality of your data.